In this video, let's solve Leetcode 84, largest rectangle in histogram. I've provided detailed timestamps for this question, listing out various questions or logical viewpoints that we are discussing about various parts of the solution. So do make use of that to navigate around and quickly make sense of all the aspects that we're discussing in this video. So let's get started. So first, let's read the question and then we'll quickly touch upon the brute force method for solving this question, and then we'll proceed and discuss the optimal way for solving this question. The question reads, given an array of integers heights representing the histogram's bar height where the width of each bar is 1, return the area of the largest rectangle in the histogram. So that's the question at hand. And we're given an example over here. So if this is the array which is given to us, which is 2, 1, 5, 6, 2, 3, then the expected output is equal to 10. And visually it's explained over here that this is the largest rectangle in terms of area that we can form. So to start with, let's try to take a deeper look at the example given to understand the question. The first thing that you can notice is that each height is represented as a bar. For example, over here you have 2, and that's what you have over here. Then you have 1, then you have 5, and then you have 6, and then 2 and 3. The second thing that you can notice is that the width of each bar is 1 unit, which was mentioned in the question. Now, to understand this question, let's think about this. What would be the maximum area that I can form utilizing this bar over here completely? Notice that I cannot extend it to the right, because if I do it in this manner, then this area over here is empty, okay? And a structure like this is not a rectangle, okay? So utilizing this bar completely, I can only form an area of 2. Now what about this bar over here? Now this bar can be extended over here, and then I can extend it over here as well. So this would be a rectangle that I can form where I use this bar. Okay. Similarly, what are some other rectangles that I could form? I could form a rectangle like this. Another one would be I could extend it and I could have a rectangle like this. Okay. And what about this bar over here? Can I extend it? I cannot, right? Because there is empty space over here. So I can only make this rectangle over here. Similarly, I could have a rectangle like this, or I could have a rectangle like this, or I could have a rectangle like this. Okay. All of these are possible rectangles. Now the question asks us to identify the area of the rectangle which has the maximum area or the highest possible area given the heights array. And visually you can see that this rectangle over here has an area of 5 into 2, which is equal to 10, and we are not able to form any other rectangle which has a higher area. For example, this rectangle over here has a width of 4 and a height of 2, so the area is just 8. So you can see 10 is still greater than 8, and that is why the expected answer for this input is equal to 10. So we have thoroughly understood the question, and again, if this was presented as a puzzle to us, and if we can just visually think about this, it's a pretty straightforward question to try out all the combinations and find the answer. But how would we do it in code? And then the second question would be, how would we efficiently do it in code? So let's get into this. So to start with, let's think of the brute force approach for solving this question. And let's use the same example which was given to us. Okay. So the first intuition that you can have is that to find the rectangle with the maximum area between any two bars, like for example, let's pick this bar and let's pick this bar. Now what would be the maximum area of any rectangle that can be formed between these two bars? It would be the width between these two bars, which is equal to 4, into the minimum height between these bars, which is 2 in this case. Okay. So this is the intuition that you can use to come up with the brute force approach for solving this question. Like you could just have 2 pointers. So one pointer is pointing over here and the second pointer is pointing over here. And then we can just move the pointers, okay? And as we move the pointers, we'll just find the minimum height between the 2 pointers, and we'll also keep a tab on the width between the 2 pointers, and then we can just multiply the minimum height into the width to get the area. And as we keep getting all the possible areas, we can just update the maximum area and finally return the maximum area. Okay, so this would be the brute force approach for solving this question. Like for example, initially the pointer is over here and over here, and in this case the area would be just 2 into 1, which is 2. And then you move this over here, okay, and the minimum height over here is 1 and the width is 2. So 1 into 2 is 2. Again, you move this pointer over here. The minimum height between these 3 is 1 and the width is 3. So you update max area to 3, and then you move the pointer. The minimum height is 1, the width is 4, so the max area is 4, and then it goes on in this manner. Okay, so one pointer was over here and we were moving the second pointer. Finally, the second pointer would reach over here, and then you cannot move it any further. So at this point, we would move this pointer, and the process again starts. We have these two over here, we move it 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 over here, and in this way, using 2 pointers, we can solve this question. But the problem is that this would have a time complexity of n square, because notice we have this pointer over here and we're doing one pass. Then we are having this pointer moved over here and we are again doing almost one pass. Okay, so in this way, this adds up to a time complexity of O of n square. And the space complexity for this approach would be O of 1, or constant space, because we are not storing anything and we are just using 2 pointers. So this would be the brute force approach for solving this question. Now the question is, can we do better? Okay, so again, a time complexity of O of n square is not the best time complexity. So yes, let's try to do better. And for that, first, let's build the intuition on how we can do better. And secondly, let's talk about these 3 points to get into the nitty-gritties. So let's start with the intuition. Let's say that there was a way to find the maximum area where you use a bar completely. Okay, like for example, you get this, which is MA, let's just call it max area bar. Let's say you can get max area bar for each bar. So you get max area bar for this bar, and then you get max area bar for this bar. Again, let's maybe go along with it visually. For this bar, the max area bar would be just 2 because you can't extend it. So you get that over here, that's 2. And then for this bar, the maximum area where we use this bar completely would be by extending it in this manner. Notice, in this case, we are using this bar completely, and it's valid to extend it in this way because all of this have bars. There is no empty space over here. So for this bar, the maximum area using this bar completely would be 1 into 6, right? Because you have 6 over here. So the width is 6 and the height is 1. So that would be 6. What about this bar over here? For this bar, I could have an area of 5, which is 5 into 1, but we want to know the maximum area where we use this bar completely, and that can be obtained in this manner. Notice in this case, I'm using this bar completely and it's valid to extend it in this manner because we have a bar over here. There is no empty space. And the area of this would be 5 into 2, which is equal to 10. So the maximum area using this bar completely is equal to 10. Now, what about this bar? So when it comes to this bar, notice that we're not able to extend it either in the left direction or in the right direction because there's empty space over here. So the maximum area which we can form using this bar completely is 6 into 1, which is just 6. And the next bar over here is 2. And when it comes to 2, notice that we can extend it to the right and we can extend it to the left till here. Okay, so the maximum area where we use this bar completely is 2 into 4, which is equal to 8. And when it comes to this bar over here, notice you cannot extend it to the left nor to the right. So the maximum area using this bar completely is 3 into 1, which is equal to 3. Now, when you're trying to solve this question using this approach, what is it that's actually happening? What is happening is, for each bar, you're setting the minimum height as the height of that bar, and then you're trying to extend it to the maximum to the left and to the right. Okay, so again, remember, in the previous brute force approach, what we did is we had 2 pointers and we tried to find the minimum height between those 2 pointers, and then we found the applicable area. But what we are trying to do over here is we are setting every height as we iterate over the heights array as the height of a rectangle, and then we are trying to extend it as far as possible to the left and to the right. Now, because the rectangle which has the maximum area has to have one of these heights, because you can't have another height, right? So whatever rectangle you form, it should have one of these heights as its height. Therefore, when you do it in this way, you are considering already all the possible heights, and then you are extending it maximum to the left and to the right. And in this way, the maximum area, or the area of the rectangle with the maximum area, has to be one of these values. And it in fact has to be the greatest value among these, which in this case is equal to 10. And that is our answer for this question. So this is the intuition for the optimal way for solving this question, because in this case, you just have to do one pass and find all these values. And then you just need to know the maximum between all these values and you can return it. So this is the intuition on how to optimally solve this question. Okay, now that we have the intuition, let's get into the nitty-gritties and think about how we can implement it. Now again, before we get into that, remember what we did is we tried to find the maximum area using a bar completely, which is the same as setting the height and trying to extend as far as possible to the left and to the right for each of these heights. And then we get the area applicable and we find the maximum area among the areas that we have calculated. So this is the intuition that we will use. Now let's get into the nitty-gritties, and for that we'll think about this approach using these 3 subheadings. Okay, so that makes it more structured and it's more helpful to think about it. So again, what we did is we set a height, like for example, we set a height, and then we had to find how far we can extend it to the left and how far we can extend it to the right. So that's what you have over here: left margin, right margin, and then you have an extra point over here, extendability to the right. I've just divided it in these 3 manners to make it easy for us to think about it. Now let's start with the first point, left margin. Pretty straightforward, right? For every bar, how far can you extend it to the left? So that's what left margin would be. Now, how do we go about it? Let's think about this. So there are basically 2 possibilities for this. Okay. Now, again, I'll just take this example, and once we are clear with the example, I'll just fill in these 2 placeholders. So this over here is our example. So initially, let's say we're doing one pass. So initially our pointer is pointing to this bar over here, which has 2. Okay. And because I don't have anything to its left, there's nothing over here, right? So let's say left margin over here is equal to 0 and the height is equal to 2. So I'm just calling it left margin, or you can call it start. Okay. And this over here is the height. So we have 0, 2 over here. And again, we're just building the intuition. After we're done with the intuition, we'll have a detailed walkthrough where we'll stitch everything together. Now let's try to identify the 2 cases involved when it comes to the left margin. And again, why are we doing all of this? Because we want to find the area of the rectangle, the maximum area of the rectangle where a certain bar is completely utilized. And that would be the height of the bar and into the width, and to find the width, we need the left margin and the right margin. Okay, so that's the higher picture. But over here, we are just trying to go deeper into left margin. So to start with, over here, we've seen there is nothing to its left. So we are setting left margin to be equal to 0. Now, when we move the pointer ahead, we come over here. Notice that 1 is a lower value than 2. So that's the case 1, where you have a lower value. The next value is a lower value. In this case, we'll have to set its left margin as 0, because notice visually you can extend it over here, right? So for this one over here, for 1, I cannot set its index. Again, let me just write the indices over here. So I have written the indices over here. So again, in this case, I could just set left margin as its index. Okay. But over here, because 1 is less than 2, I cannot just set over here the left margin as 1 itself, but rather I'll have to set it as 0, because I can extend it over here. Okay. And when we proceed, we come over here. The value is 5, which is a higher value. The next value is a higher value. And for 5, the left margin would just be its index, because I cannot extend it to the left. Okay. So these are the two cases when it comes to left margin. Now, how to take care of all of this in code, etc., we'll talk about it. But notice these two scenarios. So for a particular bar, if the value to its left is a lower value, then its left margin will be its index itself, which is what you have seen over here. Okay. And if the bar to the left of a particular bar is a greater value than itself, like the case over here where 2 is greater than 1, then you will have to update the left margin for this bar to be this one's index. So that is our first observation, or that is the first intuition that you can build. All right. So far we have talked about left margin in two possible cases. One case was something like this, where the left value for this value over here is a greater value. Therefore, we would have to extend the left margin and write this value's index or this height's index as the left margin for this height. The second case that we have seen is something like this, where the height is increasing. So over here, its left margin would be its index itself. Now, how do we take care of this? This is where we come to the second point, and I've just called it extendability to the right. And you'll come to know why I've mentioned this in a minute. But again, I've mentioned over here to the right because we'll be doing one pass from left to right, or we'll just go from index 0 to the last index of the heights array which is given to us. And we will be using a stack over here, and in the stack, we'll store two values. Okay, we'll store two values. So let me just write it in this manner and see what's happening. So initially, we are over here, and again, we don't have anything to its left. So I'll be storing, and let me write that over here. This is start and this is height. And start, you can talk of it as left margin. Okay. So initially, this has 0 because nothing is there to its left. So I'm just adding its index, and height is 2. Now I come to the next value over here, which is 1. And I see at this point that, again, our aim is to have its left margin, like we have 1 over here, and its left margin should be 0, because ultimately I'll be able to extend this one over here, which is something that we have already discussed. Now, as part of extendability to the right, notice that this bar over here, I know its left margin, I don't know its right margin yet. But because the next bar for this bar is a lower value, it has a lower value, therefore I will not be able to extend this bar. Okay, so I'll not be able to extend this bar anymore to the right, and I already know its left margin, so there is no more point for storing this in our stack. Okay, so again, what's the scenario that we're talking about? We're talking about a case where over here the pointer is pointing to 1 and 1 is less than 2. Therefore, or in other words, current height is less than height previously added to stack. Now, because this is the case, I will not be able to extend this bar to the right. Okay, and therefore there is no need for storing this in my stack. So, and I will pop this from my stack. So I'm popping it. Okay. And then once I have done that, there is nothing else in the stack. So this criteria is no longer the case. And I will add 1 to my stack. And I will add this 0 over here, which is the start or left margin of the popped value, as the start or left margin for this value, which is 0 over here. So this 0 has been added over here as 0, and I have popped this. And when I pop this, I'll also find the area, the maximum area that I can form using this bar completely, which in this case would be 2 into 1. Now let's also talk about how to get that. So again, the height is 2, we already know that. And then I just need to know the width. So that would be the meaning of the maximum height of the rectangle where this bar is completely used. Now at the moment of popping this, the pointer was pointing at index 1, okay, and its start value was 0. So all I have to do is index, which is 1, minus the start value over here, which we get from the stack, which is 0. So 2 into 1 minus 0 is equal to 2, and that's the area of this particular bar over here. Notice I just have to do the index value where the pointer is currently pointing to minus the start value which I get from the stack when I pop it. So in this way I can get the width for a rectangle which uses a bar completely. And in this case, the width of the rectangle which uses this bar completely is 1 minus 0, which is 1, and 2 into 1 is equal to 2. So in this way, we'll keep finding the area, and then finding the maximum area is pretty straightforward. Whenever you get a new area, compare the current maximum area with the new area and update if the area is greater than max area. Okay, so that part is pretty straightforward. So let's not discuss that over here. We'll just say that we find the area, and then comparing with the existing max area is pretty straightforward. So we will see that in the detailed walkthrough, but over here, let's continue building the intuition. So far we have discussed the two cases for left margin, and over here we have seen how to handle those two cases. Like, we were not able to extend this bar any more to the right, so therefore we are popping it. And there's one more reason to it. Like, when we add this bar to the stack, its start value should be the start value of the popped value. Like, this one had a start value of 0, that's what was over here, and this will be inserted as the start value for 1, which is the new height. Okay, so this is one part of extendability to the right. But let's also take a look at the next value, which is 5. And let me just make some space over here. So at this point, we only have 0, 1 in our stack, and this was popped because it was no longer required. We could not extend it to the right. And we also discussed how we got 0 over here. Okay, now we move to the next. The pointer is pointing to 5. And we would want to add this 5 to the stack. So we add it over here. Now, two things to think about. The first thing is, this one can be extended to the right because this value 5 is greater than 1. So we are not going to pop this from the stack. That's the first point. Okay. And the second point is, this is greater than 1. Therefore, the left margin for 5 will be its index itself. So 0, 1, 2, 3, 4, 5. These are the indices, right? So the left margin for this will be its index itself, because we cannot extend it to the left because 5 is greater than 1. So when I insert this to the stack, I'll have 5 as the height, and the start value will be its index, which is 2 itself. Okay. So what we have discussed over here under extendability to the right is, when we get a current height, as we move the pointer, we get a new current height. Let me just call it new current height. Now, this new current height can either be greater than the previously entered height, or it can be less than the previously entered height. So if the new height is greater than the previously entered height, then we don't need to pop the previously entered height. That's one thing. And the left margin will be the index of the newly added height itself, because we cannot extend it to the left. On the other hand, if the newly added height is less than the previously entered height, which was the case over here, in that case, we have to pop the previously entered height because it cannot be extended to the right. Like visually you can see this bar cannot be extended to the right, and the left margin of this one has to be set to the start or the left margin of the value that we are going to pop because we can extend it in this manner. So these are the two things that we have discussed so far, and I've just clubbed it as left margin and extendability to the right. So these things are done. Now the only thing that remains is right margin. So let me make some space over here and let's finish this part as well, and then we'll tie it up all together and have a detailed walkthrough. Now right margin plays a role when we want to find the area. Okay, and we have seen a taste of right margin over here. Remember, when we popped this value 0, 2 from our stack, we also had to find the area that this bar can make. What's the maximum area that we can get by including this bar completely? Okay, and the way that we did it over here was 2 into 1 minus 0. And remember, this was I because the pointer was pointing to index 1, 0, 1, 2, 3, 4, 5. These are the indices. So the pointer was pointing to 1. So that's how we get this 1 over here. And this 0 comes from here, which is the start value for this entry of height 2. Okay. So in other words, the right margin of a value that we pop, again, we have two cases over here, values that we get to pop and values that we don't get to pop. First, let's talk about this. So this was a value that we got to pop. Again, we have seen when to pop, right? When the next value is a lower height, we pop. Like for example, after 6, when we come to 2, 2 is less than 6, so we would have to pop this. And then we would compare 2 and 5, so we would have to pop this. Again, this would be a loop. We'll come to it when we have the detailed walkthrough, but we have seen that we pop when the next value is a lower value. That's something that we have already discussed, right? So when we pop, the right margin will just be the place of the pointer or the value of the pointer. That's the first observation over here. Like over here, we popped this. So the pointer was pointing to 1, and 1 minus 0, which was the start value of this, gave us 1, which is the width of this. So the right margin is just the pointer. Okay. Now again, let's see the case over here. We popped this, then we added 0, 1. We discussed how we did that. And then we added 5, 2. And because 5 was greater than 1, the index of 5 itself is the start value. We discussed this much. Now when it comes to 6, again, I would want to add it over here. And 6 is greater than 5. So the start value for this would be the index of 6, which is equal to 3. After this, we get to 2. And I would want to add 2 to my stack. But 2 is less than 6. So therefore, 6 cannot be extended to the right, and hence I would want to pop this. Okay. And when I pop this, I would want to take its start value and place it over here. But again, there's one more thing over here. We'll have to keep doing this as long as the value in the stack is greater than the new height. Because we are over here, and notice, same as 6 cannot be extended over here, 5 also cannot be extended over here because 2 is less than 5. So this also has to be popped. Okay. So next I pop this and I get 2 over here. And after that I have 1 which is less than 2, and therefore I don't need to pop this, and I take this 2 over here and I'll have to place it over here. So this entry would be 2, 2. So this is an extension of what we have discussed so far. Now coming back to right margin where we are popping, which is these two cases. Let's talk about that. First, we popped 6. Okay. And the pointer at that time was pointing over here. Remember, we got over here, and it's at that time that we saw that 2 is less than 6, because of which we decided to pop 6. And at this point, right is 4 and the start value for 6 is 3, which is what you have over here. Instead of 0, we have 3 over here, and the height is 6. So 6 into 1 is 6, and that is the maximum area that we can get where this bar is completely used. Okay, again, when you pop, you just need to take the pointer value as the right margin. So I just wanted to show that once more with one more example. And in this case also, like with this, notice the area that we want is 5 into 2, which is 10. We can see that visually. and we have the height already, which is 5, and the pointer is pointing to 4, and its start value is equal to 2, right? So 5 into 4 minus 2 is 5 into 2, which is equal to 10. So yes, in this case also, the right margin is nothing but the pointer value, which is the case when you are popping. Now we just have one more aspect left as part of the intuition, and then we'll have a detailed walkthrough where we will stitch all these intuitions together to come at the optimal approach for solving this question. So let's talk about this. What would be the right margin when we don't pop? Let me make some space over here. All right. First of all, in what scenario will we not pop? Like for example, notice this bar over here. This bar would still remain once you're done with one pass, because we only pop when the future value is a lower value. Like for example, if we had a 2 over here, then we would have popped this. Like we popped this 2 because we got a 1 over here. But in this case, there is nothing beyond it, right? Because of which we will not pop this after one pass. Now, what does this imply? Or what is the meaning of a bar being still in the stack after we are done with one pass? The meaning is that this can be extended to the right as much as possible. Alright, now let me take one more example to make this clear. What about this bar over here? This bar would never be popped, because for it to be popped, we would need a smaller bar over here. Like if we had half over here, when we get to this, we would have popped this. But because we don't have any bar which is lower than this, even after doing one pass, this bar would still be there in our stack. Now, what does this mean? It means that this bar can be extended till the end of the height array which is given to us. Okay, so how do we find the maximum area that this bar can form when it is completely utilized? For one, we know its left margin is 0 and its height is 1. So we know the maximum area that this one would form is height into the width. And for width, we would need how much we can extend it to the right and how much we can extend it to the left. Visually, we can see that it can go up to here, and we already know that its left margin is over here. So how do we do this? In this case, we would take the length of the heights array, which is equal to 6 minus 0. And in that case, you can see we get 1 into 6, which is correct because that's the area of this rectangle. Okay, so in that case, we're just taking 6 because that's equivalent to having a pointer over here. Notice when we dropped or when we popped this one, the pointer was in the next place, which is over here. Okay, or when we pop this one, the pointer is over here. And the pointer was over here when you pop this because you want to take everything up to here. Similarly, over here also, when you pop this 5, right, the pointer was over here because you want to take everything up to here. Similarly, at this point, when you're trying to find the maximum area that can be formed using this bar completely, you want to take everything up to here. So that's why it's equivalent to taking a pointer over here. And this index would be nothing but length of the heights array. Okay, and even from a pattern matching perspective, you can see we want the value 6 over here, and we do get that when we do size of the height array minus the start value. All right, so to summarize, the right margin when we do not pop is nothing but the size or the length of the given heights array. So these are the observations which will help us arrive at the optimal approach for solving this question. Let's now proceed and stitch all of these together in a detailed walkthrough. All right, so we have this heights array which is given to us, and we have discussed that we will be using a stack. So let me draw that over here, and we will be doing one pass. So for that, we will be using a pointer. Initially, our pointer is over here, and let me also write the indices 0, 1, 2, 3, 4, and 5. Now, I want to add this to my stack, and also we'll be keeping track of max area, okay? Because that's what we need to finally return. So at this point, let me say max area is equal to 0. Now, we are over here and we will want to add this to our stack. So the height, and in the stack we have always two values for every entry, height and start. Let me call it start, which is the same as left margin. Okay, you can use any terminology you want. So initially I will just add height as 2 and start value will be 0 because there's nothing to its left. We add this to our stack and then we proceed. The pointer is moved to index 1. At this point, I see that 1 is less than 2, so I cannot extend 2 any further. Therefore, I will pop this. Okay, I'll pop this and then I have nothing else left in our stack. So therefore, I can go ahead and add 1 and its start value will be this 0 which I got from here. So that would be the start value for this, and this is the entry that I make in my stack. Now this is required because we can extend this bar to the left up to here. So that is why the start value over here is equal to 0. We again proceed and the pointer comes over here. The height over here is 5 and 5 is greater than 1, which is the value I have in my stack, right? So I add 5 and the start value will be its index itself. So I add 2 over here. Okay. Again, we move forward and the pointer comes to index 3. Now again, I missed one thing. When we popped this, we also have to find the maximum area that can be formed using this bar. And that can be found as 2 into the applicable width. And again, this is the case for popping, right? Remember, right margin, there were two scenarios, popping and not popping. This is the scenario of popping. So the pointer at this point, when I popped this, the pointer was over here, which has a value 1 and its start value is 0, 1 minus 0, or I minus start, where I is the pointer. So that's how you get this. And 2 into 1 is 2. So max area at this point is equal to 2. Okay. So this should have been done over here. I forgot to mention it. And after that, we make this entry 1, 0 and we proceed. Okay. So that's how we get to over here. We added 2, 5 over here and then we move the pointer and we get to 6. Now 6 is greater than 5. 5 is the latest value added to the stack. So 6 is greater than 5. So we can just add it over here and the start value will be its index itself, which is 3. So I have 3, 6 over here. Again, I move the pointer ahead. We come over here and the value is equal to 2. Now 2 is less than 6, which means that I will not be able to extend 6 any further to the right. Therefore, I will pop this from my stack. Okay, I'll pop this from my stack, and when I do that, I have to find the maximum area I can form using this bar completely, which will be 6 into, and this is the case of popping, right? So the pointer is pointing to index 4 and the start value over here is 3. So 6 into 4 minus 3 is equal to 6 itself, and that would be the maximum area I can form using this bar completely. And 6 is greater than 2. So let me update my max area to 6. Okay. Now again, my pointer is over here and I want to add this 2 to my stack. But before doing that, I'll have to ensure that the latest added height in the stack is not greater than this value over here. But at this point, I have 5 over here and 5 is greater than 2. So therefore, I will have to pop this as well. Now when I pop this, I'll find the maximum area that I can form using this bar completely, which would be its height, which is 5, into where the pointer is, which is 4. The pointer is still over here, right? We are over here. So that's 4 minus the start value over here, which is equal to 2. Now 5 into 4 minus 2 is equal to 10. And that's the area that we're getting over here. And 10 is greater than 6. So let's update our max area to 10. And at this point, I just have 0, 1, where 1 is the height in my stack and 1 is not greater than 2. So therefore, I can add 2 to my stack. So I have 2 over here, which is the height, and the start value for this should not be 4, but rather the start value of the latest popped value. And that's this one over here, right? So this 2 will be the start value over here, which indicates that I can extend this bar till here, which is true, right? So we have discussed this. So I can extend it up to here. So that is why this 2 has to be added as the start value over here. So I add 2 comma 2 to my stack. After the pointer ahead over here, and the value is 3. 3 is greater than 2, which is what we have over here. So I can just add it over here. 3 and its index, which is 5, will be the start value. All right. So we have done one pass and we are not yet done, because notice there are still this value and these two values in our stack, which means that we have still not calculated the maximum area that can be formed using these bars completely. So we'll still have to do that. So we're done with one pass. Now let me just clean this up, and then we come to this case over here, right margin, when we did not pop, because notice these values are still in the stack, so we did not pop. So we're going to deal with this now. Now let me make some space over here. All right, so I've made some space over here. Now let's go over the stack, and our aim is to find the max area that each of these bars which are still there in the stack can form. Okay, so what about this bar over here? The max area that this bar can form is its height, which is 1, into the size of the heights array which is given to us, that's equal to 6. So this is the length or size of the given array, okay, minus what we have over here, which is the start value, which is 0. So 1 into 6 minus 0 is equal to 6, and that's the maximum area we can get by using this bar completely. And visually you can see that's correct, right? This by extending it till here and here. And again, remember, not popping means this bar can be extended till the end, like this. So this area is 1 into 6, which is equal to 6. But 6 is not greater than 10, so we don't update max area. In a similar manner, we proceed to the next element which is there in our stack, which is 2 comma 2. So that's this one over here. And let's find the max area that this bar can make, right? So that would be 2, which is the height, into the length or the size of the heights array, which is 6, minus what we have over here, which is 2. So 2 into 4 is equal to 8, and that is this area. Now 8 is not greater than 10, therefore we don't need to update it. But if we got a greater area over here, we would have updated this. Okay. Similarly, we proceed to the next element, which is 5 comma 3, and the max area that this element can form is 3, which is the height, into length of the heights array, which is 6, minus 5, which is what we have over here. And 3 into 6 minus 5 is 3 into 1, which is 3 itself. Now again, 3 is not greater than 10, so we don't update this. In this way, we are able to check the maximum area that can be obtained by using each bar completely, and after finding all the possibilities, we have seen that the maximum area that we can get is 10, and we would just return this 10. So this is how we can solve this question optimally. So notice, on a high level, we did one pass over here, and then we did a few more operations over here to take care of the elements which remained in our stack. Now, what is the space and time complexity of the approach that we have come up with? Let's quickly discuss that as well over here. Now, let's make some space to do that. So, notice the time complexity of this approach is O of n, because we are just doing one pass over here, which will be n operations, and then the elements in our stack which would remain will be definitely less than n, right? So, at max, even if you take it as n plus n is 2n, and 2 is a constant, you can avoid it, and therefore the time complexity of this approach is O of n. The brute force approach, remember, had an O of n square time complexity. But the brute force approach, which we discussed, has a constant space complexity, but this approach has a space complexity also of O of n, because we are using this stack over here, which at max can have n elements. So the time complexity of this approach is O of n, and the space complexity of this approach is also O of n, because we are using this stack. Let's now get into the code and write out the solution that we have discussed in the previous part. Okay, so again, let me just make this a little bit bigger. All right. Now, as we've discussed previously, we're going to use a stack. Okay, and for a stack, I can just use a normal array, and initially it's just empty. And we will also use a variable, let me call it max area, and initially this is going to equal 0, and finally once we find the maximum possible area, then we will just return it. Okay. Now what we will do is we will do one pass. Okay, we'll go over the heights array which is given to us, and then our aim, as we have discussed in the previous part, is to keep adding the values to the stack, but whenever we encounter a height which is lower than the height which was last added to the stack, then we will start popping. So again, we have already discussed the approach. Now let's get into the code. So I can say for I comma h in enumerate heights. Okay, so this would give me the index as well as the height in the heights array. Okay, the heights array has just values like this, the example which we have over here. Okay, so this is one example, so that's why we have to use enumerate over here so that we can get the index as well as the height. Okay, so let me just write this over here. So this is an example of the heights array which is given to us. Now as we are going over the values in the heights array, we'll have to check whether the last added item, the last added height in the stack is greater or less than the current height. Okay, and based on that we'll have to make decisions. So to start with, let me say start is equal to I, and again we will see why this is the case, because finally when we push a value, a height to the stack, we'll not only be pushing the height, but we'll also push the start, because remember we finally need to check what would be the area that we can make. And again, for example, over here notice, let's say this is the array which is given to us, and we initially push 2, then we get to push 1, but when we see 1, we see that 1 is less than 2, so we will have to pop. But again we'll come to that. But when we pop, we would want to know what is the maximum area that we can form utilizing this complete bar, and that would be the height of this bar into the possible width where this bar is completely used, and that is where we would need start, because we would just need to do index minus start to get the width. For example, in this case, when I is at 1, let me just write that over here. So I would be 1, and that's why the current height would be 1, and let's say we see that this height is less than this over here, and therefore we would have to pop. So that is one part. Now because we'll have to pop, we'll have to identify the maximum area where this bar is completely used, and that would be 2 into the width possible, and in this case we know that that's 2 into 1 because there is nothing over here. But how do we get that 1? We can get that 1 by just doing I minus start, which would be equal to, in this case, 1 minus 0, because for this particular value, when we append it to the stack, we would be appending not only 2 but also the start value as 0. Okay, now again more of that soon, but this is just an introduction. So to start with, let's say start is equal to I, and we'll have to check whether the current height which we want to add to the stack is less than the height which was previously added to the stack, because if that is the case, then we will have to pop the previously added value from the stack, and we have discussed the logic for that in detail in the previous part. So let's go ahead and make that check. So while stack, that is while the stack is not empty, and if stack at -1, which is the previous or the latest value added to the stack, and again we would be adding the index, the start value, as well as the height. So the height would be at index 1 for every element added to the stack. So if this height, that is stack at -1 at 1, if this height is greater than the current height, or in other words, if the current height is less than what was previously added, so if this is the case, then we would have to pop, right? We'll have to pop from the stack. And if that is not the case, that is if the current height is greater than the previously or the latest added height to the stack, then we would just append the current height to the stack. So let's write that first. So over here I would say stack dot append, and again we are appending the index as well as the height, and with the index will not be just appending the index but rather the start value from which we could derive the width of the maximum possible that can be formed utilizing the entire bar. So in this case, the start value would just be start and the height would be the current height, which is what we got over here. Okay, and again, this is the case where we did not have to pop from the stack. Okay, now again I need to add brackets over here as well. So this is the case where we did not need to pop from the stack. Like for example over here, let's say we already added 5 to the stack and let's say we get to 6. So at this point we would just add the index. In this case that would be 0, 1, 2, 3. So 3 would be the start value and the height would be 6. So we would just add that. But if we have to pop from the stack, like for example, let's say we are adding this 2 to the stack. So in this case, we would see that the latest added value to the stack so far, which is 6, is less than 2, because of which we would have to pop this 6 because we can't utilize 6 completely along with this bar. Okay, and again we have discussed the logic already, but the reason is that we will not be able to extend this bar completely to the right, because of which we will have to pop this. And when we pop it, and the logic for that would be written over here. So again, let's pop it. So I can say index comma height is equal to stack dot pop. And again, remember we are appending the index as well as the height to the stack. So we'll get these two values when we pop from the stack. And after we pop from the stack, we'll have to find the area using the complete height of the bar popped. Okay, so for example, in this case, if we are popping 6, we would want to know what is the maximum area that we can form utilizing this complete bar. We would want to use this complete bar and see what would be the maximum area possible. Now visually over here we can see that the maximum area where we use this complete bar is just 6, but over here how do we find that? We've got the index and the height, okay, and the area that we can form utilizing this complete bar would be the height, which we get over here, into the width applicable, which would be I minus index. Okay, so this is the interesting part. So we have I, for example, at this point I would be pointing over here, and index is something that we get from the stack. Now when we appended 6, the index would have been appended as 0, 1, 2, 3, okay, and I is pointing to 4, and 4 minus 3 gives us 1, and 6 into 1 is 6, which is correct. Visually you can see that 6 is the maximum area that can be formed using this bar completely. Okay, so this would be the area, and once we get the area, max area would just be the maximum between area and what we already have in max area. Okay, and one more important step, because we popped, we'll have to set start to index, because after popping 6, and in this case we would keep popping till this is true, therefore 5 also would be popped, right, because 5 is also greater than 2. So first we'll pop 6 and start would be set to 0, 1, 2, 3, because the index over here is 3, and then we'll pop 5 and start would be set to 0, 1, 2, the index over here is 2. Okay, so start would be set to 2, and then when we append this height over here, which is 2, to the stack, the height would be 2, but start would be this over here, 2, 0, 1, 2. And the reason for this is visually you can see that when you are forming a rectangle utilizing this complete bar, the left margin goes up to here. So that's why the start value has to be the index of this bar, which is 0, 1, 2. Okay, that's how we handle it over here. So start is equal to index, and then once we are out of this while loop, we'll just append start and the height to the stack. So this is one pass. Okay, so let me just write that over here. Okay, I've already written it. So this is one pass. Maybe I'll remove these comments. Okay, so once we are done with this one pass, we'll have to check whether there are still elements in the stack. Okay, and that would mean that those elements can be extended from their respective start till the end of the input array. Okay, so again we have discussed that, but let's implement it over here. So I can say for I comma h in stack, and for each of these elements the maximum area utilizing that respective bar completely would be its height into the length of the height array minus I. Now what is this over here? I, again, remember, is the start value which you are getting. So again, instead of I could just write start over here to make it more clear. Okay, so start is something that we are getting from the stack, and that's what we are doing over here as well, right? I minus index, where I in this case would be length at heights, because again notice, if this is the heights array which is given to us, let's take that example. So if this is the heights array which is given to us, and let me paste it over here. Now let's say I am talking about this bar, and we know that we can extend it till the end because there is nothing beyond it, right? And visually notice that this bar cannot be extended to the left. So whenever you're adding this to the stack, like after 2, whenever you're adding 3, 0, 1, 2, 3, 4, 5, 5 would be the start value for this, because 3 is greater than 2 and the height is 3. So in the stack, this bar over here would have 5, 3, where 5 is the start value and 3 is the height. Okay. Now what would be the area? Again, we are talking about the case where we are out, where we have done one pass and still elements are remaining in the stack, and this would be one of the examples. 3 would still be there once we are done with the pass. So how do we find the maximum area that this bar can make? For that, we'll have to do this height, which is h, into length of heights, which in this case is 6. Okay, so this would be, let me write that, 3 into 6 minus start, which in this case would be 5, and this would be 3 into 6 minus 5 is equal to 1. So 3 into 1 is 3. Okay, so in this way you can find the area for every bar which remains in the stack, which means that it can be extended till the end by doing h into length of heights minus start, and then we can just say max area is the maximum between what we already have in max area and the area that we found over here. And once we are done with this, we can just return max area, which is something that we have already written over here. Okay, so that's it. So this is how we can solve this question. Now let's go ahead and run this code and see if it's passing all the test cases. Okay, it's working. Now let me submit it, and you can see that it's working. It's passing all the test cases. Let's also quickly discuss how you can implement the code in JavaScript. Now I don't want this video to be too long, so I've already written the code over here, but let's quickly walk through the areas where students might find certain difficulties. So I have the code over here. Now let me make this a little bit bigger. Okay, and we have our largest rectangle area function over here, and as we have discussed, we're going to use a stack, and for implementing a stack I can just use an array. And then we have a variable max area which is initially set to 0, and we will just return it ultimately over here. Okay, and after this we're going to do one pass through the heights array which is given to us, and initially we will set start to equal I. Now again, let me just pick this example over here which we have. So if this is the heights array which is given to us, okay, so initially start is equal to I, which is 0, and this while loop will be false because we have not added anything so far to the stack. So let's come to this in a while, but if this is false, we'll come over here and we will push to the stack an array with two values. So the start value over here and the height at the current index. So we will be pushing 0, 2 to the stack when we are over here. Okay, and then let's say we proceed over here, we come to 1, and at this point we see that the previously added height to the stack is greater than the current height. Okay, so this is the previously added height to the stack. So stack dot length minus 1, stack at this index will give me the latest added array to the stack, and in the array we have index or start at index 0 and height at index 1, which is what you can see over here, right? So that's why this over here will give me the latest added height to the stack, And if that is greater than the current height, which is what you see over here, 2 and then 1, then we will have to pop the previously added height to the stack. And again, we have discussed the logic for this, and in one sentence the reason is that we'll not be able to utilize this complete bar and extend it to the right to form a new rectangle. Okay, so that's why we'll have to pop this one. Now when we pop this, we'll get both its start value, which is what we have over here, and its height. Okay, now you can just call it index or you can call it start. So once you get this, we can find the maximum area that you can form utilizing this complete bar. So that's the interesting thing. Okay, so we are utilizing the complete bar which we are popping, and we would want to know what's the maximum area that we can form, and we can find this by doing this height multiplied by the width. The width would be the maximum width where the current bar can be completely used, and to find that you can just do I minus index, because we'll be storing index in this manner. Like for example over here, it's a trivial example, I would be 1 and index is 0, because we saw that we added 0, 2 initially. So 1 minus 0 is 1, so this is 1 minus 0, and height is 2. So 2 into 1 gives us 2, which is the maximum height that this bar can form. That's visually very clear. Okay, and we would be setting start to index whenever we pop. Again, let's take one more example to make this more clear. So let's take this part over here where you have 5 and 6 and then you have 2. Okay, so when you get 2, this over here would be true because 6 is greater than 2 or 2 is less than 6. This means we'll have to pop this 6 because you can't extend it to the right and make a rectangle that completely uses this bar. Okay, so that's the first point. Now when we pop 6, we'll get the index and height. So in this case, now when you walk through this, you'll see that when you add 6, you'll have pushed 0, 1, 2, 3. So that's index 3 for 6 and the height is 6. So 3, 6 would have been pushed to the stack. Okay, now because we are at 2, we'll have to pop this 6. So we get 6, which is this height over here, and I would be pointing over here, right? 0, 1, 2, 3, 4. So I is equal to 4. And start would be equal to 3, or index in this case would be equal to 3. Now notice that 6 into 4, which is where I is, minus 3, which is the value of index. This gives me 6 into 1, which is equal to 6, and that is the maximum area which can be formed where this bar is completely used. Okay, and then we would be setting start to index, which in this case is equal to 3, because for 2, I'll need to insert along with 2 when I'm doing stack.push the start value such that I'll get the left margin, which I can later use to find the maximum width where this particular bar is completely used. Okay, so in this case we would be popping 6, and again when we come over here, we'll see that it's still true because 5 is greater than 2 or 2 is less than 5. So we'll still need to pop this one, and when we pop it, we'll find the area. Okay, and then we'll set start is equal to index, and the value index over here would be 0, 1, 2. So start would be set to 2, and after that we see that 1 is less than 2, so no more popping, and we will come over here and we'll be pushing to the stack the height 2 and the index 0, 1, 2, which is the index of this particular bar. Okay, so 2, 2 would be pushed to the stack. Now this is useful because in a future instance you can use it to find the maximum area that you can form which completely uses this particular bar. So that is what we are doing over here. We are setting start to index whenever we pop, and ultimately we will push the new height and the start value to the stack. Okay, so that's this part over here. We have done one pass. Now as we have discussed in the logic part, after you're done with this, you may still have some more values in the stack So for each of those bars, we'll have to find the maximum area that can be formed. Okay, so again we'll keep taking one by one the values from the stack. So we are doing start comma h of stack, so we'll get the start value as well as the height of the values remaining in the stack. And to find the maximum area that can be formed using those values, we can just do height into height.length minus start. Okay, now again let's take an example to understand this. So let's say we have 3 over here. Once you're doing one pass, 3 would still remain in the stack because it's the last value, and we are only popping whenever the future value is less than it. So 3 would still be there in the stack. Okay, now how do we find the maximum area where this bar is completely used? For that, you can just do, let me write that over here, 3 into heights.length would be 6 because there are 6 elements in the heights array which is given to us, minus the start value. And when you add 3, like after 2, you would be adding 3, and 3 is greater than 2, so you would just do stack.push start comma heights at I, and start at this instance would be equal to I. So that means whenever we added 3, the start value which is pushed to the stack would be its index, which is equal to 5, and that is what we're getting over here. Okay, so heights.length, which is 6 minus 5. So this is 3 into 6 minus 5, which is equal to 3, and you can see visually that that is the maximum area this particular bar can make when it is completely used. So again, quickly recapping, after the pass, the values that remain in the stack are the bars which can be completely extended to the right. And to find the maximum area that we can get when that particular bar is completely used would be the height of the bar into heights.length minus the start value when we added that particular bar to the stack. Okay, now let's take one more example. Like what would be this in the case of this 2? This 2 would still be there when we, after completing one pass. Okay, so again we'll have to find the maximum area that we can form when this 2 is completely used. So for that we'll have to do 2, which is the height over here, into heights.length, which is 6, minus the start value of 2. And again remember, when we added 2, we would have popped 6 and 5, and therefore the start value would be the index over here, which is 0, 1, 2, 0, 1, 2, right? So 2 would be the start value or the index that we added along with this 2 when we added it to the stack. So that's what we're getting over here, and therefore the maximum area that this bar can make when it is completely used would be 2 into 6 minus 2, which is 2 into 4, which is equal to 8. And visually you can see that that's correct. That's extending it over here, right? So that's 1, 2, 3, 4, and into 2, that's 2 into 4, which is equal to 8. So this is how you can find the area for each of the bars which remain after doing one pass, and then this is normal, like we're just finding the maximum area among all the areas that we get, and finally we are returning the maximum area. So this is how you can solve this question in JavaScript. Now let's quickly submit this and see if it's passing all the test cases. And you can see that it's working, it's passing all the test cases. If you're trying to learn data structures and algorithms through a structured step-by-step approach, do check out my best-selling DSA Udemy course. In this detailed hands-on course, you will dive deep into key data structures, powerful algorithmic techniques such as backtracking, dynamic programming, greedy strategies, crucial patterns such as sliding window, two pointers, merge intervals, and solve numerous Leetcode coding challenges to sharpen your problem solving skills. Each concept is simplified with bite-sized animated lessons, relatable examples, and step-by-step coding demonstrations. By the end of this course, you will develop deep confidence to tackle DSA coding problems. To know more about this course, click on the link in the description and take your problem solving skills to the next level.